This is the second video in BC Calculus on improper integrals, section 8.4 in our textbook. And we are going to pick up with looking at when both the upper and the lower limits of integration are positive and negative infinity. And so as previously discussed in the first video, this is going to have to be separated into two integrals that end and begin at the same value, somewhere between negative infinity and positive infinity. So you can choose anything you want for that number where you split it. It is really and truly up to you. Honestly, when I'm choosing places though, I would want to choose something easy to substitute in. So something like 0 or 1 would probably be a good place to split it. So we're going to try it. My handwriting is not doing very good here. We're going to try it at 0. So first thing that I'm going to do is I would have to look at e to the x over 1 plus e to the 2x. I'm going to try to integrate that. That's going to be a u substitution problem. So let me come over here to the side, and I'm going to work that with u would be e to the 2x. Scratch that. That's what u squared is. So u squared would be e to the 2x or e to the x quantity squared, which means that u would be e to the x, which means that du is going to be e to the x dx. So this, and this applies to both my integrals, this is my du, and this is u squared. So that makes that first integral, for example, the limit as, we'll say b goes to negative infinity of the integral from b to 0 of 1 over 1 plus u squared du. And then we'll worry about the other one with the 0 to infinity in just a minute because it's going to be a lot of the same work till we get to the end there. So that integrates back to inverse tangent. So this would be the limit as b goes to negative infinity of inverse tangent u. Now, I do, even though this is u substitution, I did keep those boundaries of b to 0 on there, but those are x values. They're not u values. I would not suggest trying to translate those into u values because of the whole limit thing in front. So what I would suggest is I would actually rewrite this now back in terms of x instead of in terms of u. So this would be inverse tangent of e to the x from b to 0. So that would become the limit. The limit as b goes to negative infinity of inverse tangent of e to the 0 minus inverse tangent of e to the b. So e to the 0 is going to be 1, inverse tangent of 1, so that would be the angle that has a tangent value of 1, that's pi over 4, minus inverse tangent of e to the b. And so if b is negative infinity, that's going to be 1 over e to the infinity. So that would be pi over 4 minus inverse tangent of 1 over e to the infinity, which is 0. Inverse tangent of 0 is 0, so our answer for the first integral is pi over 4 minus 0, or pi over 4. Now let's go back up here and look at the other guy, and I'm going to do him in red. So this would be plus the limit, and since we've already used b for the first half, you can choose some other constant. You can choose c, you can choose d, it really doesn't matter. So we'll say as c goes to infinity of the integral from 0 to c of 1 over 1 plus u squared du. So we can really skip down to right here where this would be plus the limit as b goes, not b, excuse me, goes to infinity of inverse tangent of e to the x from c to infinity. So scrolling down, the next line there, I kind of don't have room for it, but I'm just going to add it on to the amount that we've already found. So this would be the limit as c goes to infinity of the inverse tangent. Let's scroll back up here and look at the mistakes that your teacher has made. So we had from 0 to c, and then here I changed it to c to infinity. So this needs to say 0 to c. Okay, hopefully maybe you caught that. So I've got inverse tangent of e to the c minus inverse tangent of e to the 0. Now we already know that e to the 0 is 1. Inverse tangent of that is going to be pi over 4. So we have from the first half of the problem, the pi over 4 there. And then out here, we would have inverse tangent of e to the infinity, and then minus pi over 4 from inverse tangent of e to the 0. So e to the infinity is going to be infinity. We looked at this in a previous problem, so inverse tangent of infinity, that happens at pi over 2. So we end up with pi over 4 plus pi over 2 minus pi over 4 for a final answer of pi over 2 for the value of that integral. Hopefully you were able to follow all of that. All right, so that is just one scenario of improper integrals, is when either of your boundaries or both of your boundaries are some form of infinity. But other improper integrals could occur anytime that your integral has an infinite discontinuity, either at one of your limits of integration or somewhere along the way between the limits of integration. So that means if you have a vertical asymptote on your function somewhere on one of your boundaries or in between your two boundaries, then that's also considered an improper integral. And so what you have to do is you would have to split it up. That mostly applies to something like this, where we would have to chop it, kind of like what we did in the last problem there with the negative infinity to the positive infinity. But we treat it the same way that we were treating those, where we still just treat it as a limit problem. So for example, here I have the integral from 0 to 1 of dx over the cube root of x. So if I was to just substitute 0 into that function, I'm going to have a vertical asymptote at x equals 0 because the denominator is undefined there. So this is an improper integral situation. So my limit then, instead of 0 being the boundary down there, it's going to be the limit as b goes to 0 of the integral from b to 1. And I'm going to rewrite that as x to the negative 1/3 dx so that I can think through the reverse power rule with that guy. So that's going to be the limit as b goes to 0. If I reverse the power rule, add 1 to the exponent, so that becomes x to the 2/3. And my coefficient is 3/2 from b to 1. So that's the limit as b goes to 0 of 3/2, I don't know why that got cut off, times 1 to the 2/3 minus 3/2 times b to the 2/3 power. Now, the nice thing about when we integrate is that that x is no longer in the denominator, so I don't have a 0 issue anymore. So I can easily substitute 0 in for b now that I've integrated the problem. So the first little part there, 3/2 times 1 to the 2/3 is just 3/2. And then this would be minus 3/2 times 0 to the 2/3, which is just 0. So your final answer for that integral would be 3/2. So see, these are not really hard problems, and to be honest, you could probably think through just working it without the whole concept of the limit, but they do want you to understand that there are issues with these functions, either at their boundaries or at some place along the way in between the boundaries. And so writing the limit notation like that is just kind of your way of recognizing or acknowledging the fact that there is a vertical asymptote of some sort, or that a boundary is infinity or something like that. So I would like for you to pause the video, and I want you to give example 7 a try. Okay, so hopefully you at least got yourself down to the point where you had -1/8 plus 1 over 2 times 0 squared. And the issue with the 1 over 2 times 0 squared is that that's going to be undefined because there would be a vertical asymptote on our integral function, the -1/2 x to the -2, that we can't really make go away. So what that means is because part of our answer is undefined, this would be a divergent integral, and so we would actually not be able to evaluate it. All right, so here is another situation where we're looking at the same function again, but we're going from -1 to +2. Now, the boundaries themselves, the function does exist there. You can see that if you substitute -1 into 1 over x cubed, you would get -1. If you substitute 2 in, you would get 1/8. But along the way, at x equals 0, we have a discontinuity of a vertical asymptote. So we actually have to split that up into the limit as b goes to 0 of the integral from -1 to b of dx over x cubed plus, and we'll do a different color here, the limit as c goes to 0 of the integral from 0 to 2 of dx over x cubed, like that. Now, so then you would work the purple integral and then you would work the blue integral and add those two together. Now, what we happen to know from the previous problem is that this guy diverges. Well, if a portion of it diverges, that means the entire thing, the whole integral from -1, why I put a 2 there, I don't know, -1 to 2 of dx over x cubed diverges. All right, so the last one that I want to look at is a situation where a doubly improper integral. So that's, again, when both boundaries would create situations where it would be improper. So both 0 would give me an undefined function, and then of course the infinity is an issue that we've previously discussed. So this would be another one where you would need to split it up somewhere between 0 and infinity. The next easy number, since 0 can't be used, would be to split it at 1, I think. So I would do the limit as b goes to 1 of the integral from 0 to 1 of dx over the square root of x plus 1, and then add to that the limit as c goes to 1 of the integral from 1 to infinity of dx over the square root of x times x plus 1. Now, I want you to try to pause the video and see if you can give this one a try, because this is a really good challenge question test. I've kind of already set it up for you. I want you to see if you can work it out, and you will actually be able to get an answer. And here's your hint. It's going to require u substitution. Okay, so I started with figuring out my u substitution. I made u be the square root of x, which means that u squared would be equal to x. du would be 1 over 2 square root of x dx, or 2 du is equal to the square root of x dx. So u substitution on my original integral would give me 2 du over u squared plus 1, which integrates back to 2 inverse tangent of u, or 2 inverse tangent of x. So scrolling back up to my problem, I did all of my red for the integral from 0 to b and purple for c to infinity. The red ended up working out to be pi over 2, and the purple ended up working out to be pi minus pi over 2. Put it all together, and you get a total value of pi for that integral. So that concludes improper integrals for us.